What is going on, everybody? Welcome to my video on how to design a supersonic airfoil. In part 1 we'll be looking at calculation of lift and drag forces, and in part 2 we'll be looking at a CFD simulation. So in commercial jets, an airfoil is typically shaped, as you all know, but in a supersonic flow the idea is to create shock waves and to raise the pressure such that a lift can be done on the object. So in this design we'll be looking at this airfoil here. It has an angle of attack as shown and an airfoil angle which is fixed. We have pressure acting on all faces which we need to calculate. There'll be a force perpendicular and parallel. And then from that we calculate lift and drag on the object. Here are some relations for supersonic flow which you must have seen before in a course for compressible flow, and the idea is that we'll be using these forces to calculate lift and drag on the airfoil. So let us get into the design of an airfoil and how to solve for flow. So we have this example here. The angle of attack is 7 degrees, the air pressure is 69,000 pascals, and it is flying at Mach 2. The airfoil angle is fixed at 12 degrees. So you can see my drawing over there. I have an airfoil, and then from that I can then calculate my angle of attack and airfoil angle that's fixed, and then from that I can get my Mach number and my pressure value. It's all given to you in the problem. There's temperature given as well, just in case we need it for CFD validation in part 2. I'll label my faces as shown over there, and the goal is to calculate the pressure values. We have an oblique shock on phase 2, and then we have expansion waves everywhere else because of the flow is turning a convex corner. You can see my problem on the blackboard as shown over here. So from that we can then move on to our phase 1. The flow angle over there is 1 degree because it is 7 minus 12 over 2. Your Mach 2 will be lesser than Mach 1 because it's being expanded a little bit. It'll actually be more, not less than Mach 1. So we have Mach 1 is more than your Mach infinity. You find your pressure ratio, and then you find your stagnation pressure, and then from that we can find your Mach number which exceeds Mach 1 because the flow is expanding, and then from that we can calculate our pressure value. So pressure at 1 is shown there. At my next location, which is the top right corner, you can see my turn angle in the same way, and then I find my Mach number, get my stagnation pressure, and then my pressure value. You can then see that I've calculated my pressure on the top faces, P1, and then my next pressure over there. And now we need to look at the bottom face. At location 2 we have an oblique shock because the turn angle is more. It's also a concave corner, so you have to find for your Mach numbers over there. You solve for your Mach 2 behind the shock, which will be lower than Mach 1, which is at 2, and then I find my stagnation pressure and my pressure at my face over there. Next up we have the back face, the bottom right. So I find my turn angle in the same way. I use my expansion wave relations to solve for my pressure value, and then you have your pressure over there. So now we have pressure values at all faces, as can be seen, except my location 4, so at the bottom face, right? So now we have all pressure values, and then from that I can solve for my forces. So for the positive force I can simply add my pressure and take the average value. We can assume that the pressure values are acting on the face at all points. We can then get the values there. And then for the force parallel we can simply do a tan angle because of geometric relations. We can then solve for your force parallel as shown. So when we have that, we can then solve for my lift and drag forces. We have my perpendicular and parallel force there. We have the angle of attack is given to us, so we can use that to calculate lift and drag. Your lift force will be your parallel force cosine of alpha minus your other force sine of alpha, and then you do the same with the drag. So for my lift force I have cosine of alpha because of the x component pointing to my right, and then you have a minus there because the y component is pointing down. You do the same thing with the drag force because the x components and y components are pointing in the same direction there. And for the lift force, it is pointing down because of my negative y value. So simply put, I can solve my lift force. My lift coefficient is given by half rho v squared times a times cl is my lift force, and then I can solve for my speed because it is Mach number times my speed of sound. And then from that I can then solve for my CL, which turns out to be 0.29. My drag coefficient is done the same way. It'll be 0.07. So from that you can have my values for lift and drag coefficients are solved over here. So from that, now I will explain what happens in the flow just to give you a better understanding of it. So we have my free stream over there. You have an expansion wave here because the flow is turning a convex corner. And then we have expansion wave at the top because the flow is turning again. So the Mach number will speed up as you go from left to right. Below we have an oblique shock because the angle is steeper, and then we have the concave corner, and then the pressure is expanding over there. And then we have another expansion wave as shown over here. So we have the idea that you have a higher pressure at the bottom and a lower pressure at the top. And all the pressure values point on the faces because of the fact that pressure is scalar as opposed to a vector. The idea is that the Mach number will be a bit lower at the bottom because of the fact that the pressure is more, and pressure and velocity have an inverse proportionality. So over there, my values can be seen over here in my summary. I've solved for my CL and CD. Thank you for watching. I hope you guys learned something about supersonic airfoils. And in part 2, we'll be looking at a CFD to look at the flow physics in greater detail and to validate my results in part 1. I'll see you guys for part 2. Stay tuned. Take care. Bye-bye.